the next section of this chapter, next and the last section of this chapter. It is 2.10, a Cauchy sequence. A Cauchy sequence. And the definition is that let Sn be a sequence of real numbers, be a sequence of real numbers, then Sn be a sequence of real numbers, then sequence Sn is called a Cauchy sequence if for any epsilon greater than 0 there exists a positive integer n such that there is a positive integer n such that the difference Sm minus Sn is less than epsilon, and it should be true for all Mn. It should true for all positive integers Mn such that Mn are greater or equal the positive integer n. It means that the meaning is that is sequence Sn is Cauchy if Sm and Sn are close when M and N are very large. Right? So sequence Sn is Cauchy if these two terms Sm and Sn are very close for very large M and N. Right? So the theorem is that if the sequence of real numbers, if the sequence of real numbers Sn converges, then the sequence Sn is a Cauchy sequence. It means what? Every convergent sequence is a Cauchy sequence, and it is very easy to prove. It means that every convergent sequence is a Cauchy sequence. And the proof is very easy. As Sn is a convergent sequence, so let me consider the limit of sequence Sn is L. Right? So it is easy to say. And by the definition of limit of this sequence, it means that for any given epsilon greater than 0, there exists a positive integer n such that the difference of the nth term and L is less than some epsilon, and it is true for all n greater or equal n. Right? So for simplicity, choose this n to be k for simplicity, because we have to use the m and n for this part to show sequence is Cauchy. So let me consider m and n to be greater or equal positive integer n, and the difference Sm minus Sn is, so it can be written as Sm minus L minus Sn plus L. So this can be written as difference Sm minus L plus Sn minus L or L minus Sn. And as sequence Sn is convergent, so this thing is less than epsilon and this thing is less than epsilon. So as the addition will come out to be 2 epsilon. So I adjust this epsilon to be epsilon by 2. So it is epsilon for all mn greater equal n. So as it is a convergent sequence, so the difference will be definitely less than epsilon, and we can say that is the difference Sm minus Sn is strictly less than epsilon for all mn greater equal n. And by the definition of Cauchy sequence, we can say that sequence Sn is a Cauchy sequence. Right? And the next theorem is, the statement is, if sequence Sn is a Cauchy sequence of real numbers, Cauchy sequence of real numbers, then the sequence Sn is bounded. So we have already shown that every convergent sequence is bounded. We have now shown that every convergent sequence is Cauchy, and now we have to show that every Cauchy sequence is a bounded sequence. Right? So it is not that much difficult part. We just have to follow the definition. So for given epsilon, so let me choose epsilon to be equal to 1 and choose a positive integer n, so that Sn is Cauchy. Sm minus Sn is less than epsilon. Epsilon is, we have chosen it to be 1 for all mn greater equal n. So what we have written, remember this thing, what we have written, Sm minus Sn is less than 1 for all mn greater equal n. So in particular, let me choose this n to be equal to this. Why? Because Sn is Cauchy sequence, that means this hold for all mn greater equal n. So in particular, let me take this n to be equal to this. So then Sm minus Sn, so I have written this n to be exactly equal to this large n is less than 1, and it is true for all m greater equal n. Right? So as m is greater equal n, so this implies if I consider Sm, so it will be, I have made the adjustment Sn plus Sn, and this thing will be less equal modulus Sm minus Sn plus modulus Sn, and it is true for all m greater equal n. As this is the adjustment, so by star I can write this thing to be strictly less than 1, and this thing is modulus of Sn. I have used the equation star here. Right? So now it means modulus Sm is this thing. So now let m is maximum of modulus S1, modulus S2, as these are finite terms, modulus Sn minus 1. M is maximum of S1, S2, Sn minus 1, as these are finite terms. We have defined m to be maximum of this thing. So then this modulus of Sn will be, if we have chosen this to be maximum, so it will be less than this m plus 1 plus modulus of sequence, modulus of Sn. Yes, so it implies that as it is absolute value of the nth term, it is some fixed real number which is maximum of this n minus 1 terms. So it implies that this thing is, it is Sm, so says that it is bounded. It implies that this thing is bounded. That means sequence Sn is a bounded sequence, right, as it is true for all m greater equal n. So every large mth term is bounded by this real number. So the next theorem, if sequence Sn is a Cauchy sequence, of real numbers, then sequence Sn is convergent. So this is the theorem that every Cauchy sequence is convergent, right? And the proof is a Cauchy sequence of real numbers, then it is convergent. So we have to show sequence Sn is convergent. So let sequence Sn is a Cauchy sequence. As it is a Cauchy sequence, so by previous theorem, what is there in previous theorem? This mth term is bounded, right? And it is true for all m greater equal n. So it does not mean it is comparable, or it is can we compare this thing with something limit superior and limit inferior? Limit superior of sequence Sn, can we compare this thing? Right, as it is a bounded, so revise some or recall some results from the limit superior and limit inferior. So this thing is nothing but limit of least upper bound of Sn, Sn plus 1 and so on, right? So by previous theorem, it is bounded and convergent and is convergent also. So it implies that by previous theorem, the limit superior of sequence Sn and limit inferior of sequence Sn are the real numbers. That means limit superior and limit inferior for the sequence Sn exist and they are to be a real number. And what we have to show? To show sequence Sn is convergent, it is sufficient to show the limit superior of sequence Sn is same as limit inferior of sequence Sn. And we have seen the result that if the sequence is convergent, then limit superior is same as limit inferior, and it is also same as limit of the sequence Sn, as it is a convergent sequence, right? So we have to prove this thing. Since for a sequence Sn of real number, we know that limit inferior of Sn is always less equal limit superior of Sn, right? So to show this thing, what we have to show? So we have to show that the other side, that means limit superior of sequence Sn is less equal limit inferior of sequence Sn, right? So we wish to this thing, we have to show this thing. So as sequence Sn is Cauchy, so by the definition of Cauchy sequence, it means that for given epsilon greater than 0, it means that for given epsilon greater than 0, there exists a positive integer n such that this thing Sm minus Sn is less than epsilon for all Mn greater equal this large n, which is positive integer, largest positive integer, right? And and for simplicity, this epsilon have to be chosen to be epsilon by 2. So for particular, for this n equal to this n, so it is Sn minus Sm is less than epsilon by 2 for all m greater equal n. Sorry, for all n greater equal n. But what does it means? It means that I can write it as, we can write it as Sn minus epsilon by 2 less than Sn less than Sn plus epsilon by 2. So that is Sn minus epsilon by 2 and Sn plus epsilon by 2 are, this is lower bound and this is upper bound for the sequence Sn. So it means that are lower bound and upper bound for all n greater equal n, upper bound for the sequence Sn plus Sn plus 1, Sn plus 2 and so on respectively, right? Respectively. Therefore, if n is greater equal n, our upper bounds, lower bounds and upper bounds. So for n greater equal n, it means that Sn minus epsilon by 2 is, as it is a lower bound, so it is less than or equal to greatest lower bound of the set Sn plus 1, Sn plus 2 and so on. And we know that the greatest lower bound is always less equal the least upper bound of the same set, and the least upper bound of this set will be less equal Sn plus epsilon by 2, as it is an upper bound for this set, right? As it is an upper bound for this set. So it implies that therefore uh, if we add epsilon by 2 throughout this equation, or if we add epsilon, so then what we can have, this so then list upper bound of Sn plus 1, Sn plus 2 minus greatest lower bound of Sn plus 1, Sn plus 2 and so on. This thing will be less equal epsilon. Is it true? This is why, since why this is so. Leftmost and rightmost ends of equation double star differs by epsilon only. So the only difference of epsilon on the left and on the right. So if I add epsilon on this thing, so it will be, the relation is less equal, so it will be a greater equal, and this is the thing. So therefore this can be written as the least upper bound of sequence Sn plus 1, Sn plus 2 and so on will be less equal a greatest lower bound of Sn plus 1, Sn plus 2 and so on, plus this epsilon, and as epsilon is arbitrary, so it means least upper bound of Sn plus 1, Sn plus 2 will be less equal epsilon is arbitrary and letting n tends to infinity. So n tends to infinity. Greatest lower bound of Sn plus 1, Sn plus 2 and so on, plus epsilon. So it is nothing but limit superior of Sn is less equal limit inferior of Sn plus epsilon, that is limit superior of Sn is less equal limit inferior of Sn. So therefore what was that equation? So we have that equation 2 and we call it as equation 3. Therefore by 2 and 3 limit superior of sequence Sn is same as limit inferior of sequence Sn, and therefore sequence Sn is convergent.